The more we learn about the immense mysteries of space, the more questions we have. We are attempting to understand the nature of everything, its location, its origins, and how it all started as we investigate the cosmos. Through this journey, we arrive at the same grand mysteries regarding the ultimate nature and origin of the universe. Regardless of the depth of our investigation, those same questions persist. The elements that comprised our starting point were non-existent at one point in time. What then was the process of their creation? Now, the fundamental question at the end of the day is, how did something come from nothing? What was the Big Bang, and how did the universe form out of nothing? It is important to understand not only where things originated, but also how they came to be, which makes this question important. This question remains, even though science has come a long way, at least up until today. My name is Rahul, and you are watching A consistent picture becomes apparent when we look out into the vastness of the universe and take into account all the observations we have made. With a hot Big Bang that occurred approximately 13.8 billion years ago, our universe is primarily composed of matter and is governed by the same laws of physics everywhere and at all times. It is shaped by the laws of general relativity. It is expanding, cooling, and subject to the influence of 27% dark matter and 68% dark energy, with the remaining components being radiation, normal matter, and neutrinos. Currently, the universe is made up of planets, stars, galaxies, heavy elements, and, in one particular location, intelligent life with sophisticated technology. These structures developed through cosmic evolution. They were not there from the start. In a major scientific breakthrough, researchers in the 20th century recreated the timeline of how our universe changed from being primarily composed of hydrogen and helium and mostly uniform to having rich structures and other complex structures. Rewinding from today to the beginnings of any particular structure or element brings us eventually to a point where our knowledge breaks down, at least for the time being. Subsequently, we can reflect on what we have and ask ourselves how it got here and whether it could have started from nothing. Without further delay, let us explore this mystery in great detail. The complex molecules that give rise to life, as we know it today, must have originated from the atoms listed in the periodic table, which are the basic components of all normal matter in the universe today. These atoms were absent from the beginning of the universe, meaning that numerous generations of stars were necessary to produce them. After that, these stars would die and use the byproducts of their nuclear reactions to resurrect themselves. The formation of planets and the complex chemistry required for life would not be possible without this stellar life cycle. The gravitational attraction of small galaxies and star clusters brings them together to form larger galaxies and starts new rounds of star formation, which is how modern stars and galaxies are formed. Because dark matter halos must form early in order to prevent star-forming events from expelling matter back into the intergalactic medium, this process depends on pre-existing collections of mass formed through gravitational growth. The formation of the cosmic microwave background and the light elements produced during the Big Bang depends on the proper interactions between radiation, dark matter, and normal matter in order to achieve this delicate balance. Prior to the complex formations we observe today, initial seed fluctuations or imperfections in density had to be present in cosmic structures in order for the abundance patterns to be observed. This calls for the development of dark matter and the establishment of the initial mass of normal matter, in addition to the mechanisms that produce these defects. These three basic components were vital during the Big Bang's early phases and had a significant impact on how the universe developed into what it is today. Given the existence of matter, space-time, the laws of physics and energy itself, we probably need to include these as necessary components that must somehow come into existence. Fundamentally, these are the new, as of yet unexplained entities that have to somehow materialize when considering the question of whether a universe can arise out of nothing. We have to go all the way back to the very early universe in order to achieve an imbalance between matter and antimatter, a time when our knowledge of physics becomes extremely hazy. As currently understood, there is a symmetry between matter and antimatter in the laws of physics. The amounts of matter and antimatter that are created or destroyed are equal in all known reactions. But the process of creating a matter-antimatter asymmetry had to occur in the early universe, which started in a very hot and dense state, where both matter and antimatter could be produced in large quantities. We do not know the exact scenario that played out in our young universe, even though there are many ways this could have been accomplished. All the methods that have been suggested, however, have three things in common: an out-of-equilibrium set of conditions which naturally arise in an expanding, cooling universe, a mechanism to generate interactions violating baryon number, which can be achieved both via scenarios beyond the standard model and through Sphaleron interactions within the standard model, and a way to induce enough C and CP violations to produce a significant matter-antimatter asymmetry. The elements required for these processes are included in the standard model, but the quantities it offers are insufficient when comparing a universe with a symmetric distribution of matter and antimatter to a universe that contains nothing. Under such circumstances, the universe most likely began from nothing, though the exact process is still unknown. Similarly, there are a plethora of reasonable ways to produce dark matter. Even though a great deal of research and testing have shown that dark matter cannot be composed of particles from the standard model, its actual nature necessitates new physics beyond what is currently understood. There are two possible origins: either the particles were created thermally in the early hot universe, and some of them survived in complete annihilation like the lightest supersymmetric or Kaluza-Klein particle, or they were produced during a phase transition that occurred during the expansion and cooling of the universe and pulled massive particles out of the quantum vacuum like the axion. There is a chance that a new kind of neutrino will emerge, perhaps in the form of a sterile neutrino that can combine with known neutrinos or appear as a heavy right-handed neutrino alongside conventional neutrinos. A gravitational phenomenon that produces an ultra-massive particle, such as Wimpzilla, is another factor to take into account. The question that needs to be answered is, given that the early universe appeared to function well without dark matter, why does it exist today? Dark matter must have been created by some mechanism where none had previously existed. That being said, energy is needed in each of these situations. Thus, the question that needs to be answered is, where did all that energy come from? The prevalent theory regarding the universe's pre-Big Bang origins, cosmic inflation, states that energy did indeed originate from nothing. This concept, often referred to as a universe from nothing, necessitates some explanation. There must be an explanation for this idea, which is sometimes referred to as a universe created out of nothing. We are frequently presented with two choices when we consider how the universe came to be. The first is making assumptions and claiming with certainty that something must have been the way it was from the beginning. The universe had certain properties at birth, referred to as initial conditions, without providing adequate evidence or more explanation. Theoretically speaking, this strategy amounts to surrendering in physics, or we could take the route taken by theoretical physicists, trying to come up with a theoretical mechanism that makes sense of these initial conditions. To do this, specific predictions that deviate from the accepted theory must be derived, and the critical parameters must then be measured through experiments. Taking the latter approach led to the development of the concept of cosmic inflation, which fundamentally changed our understanding of the origin of the universe. The hypothesis of inflation implies that the hot Big Bang may have been preceded by a phase in which an incredibly high energy density existed in the fabric of space itself, as opposed to extrapolating the hot and dense state back to an infinitely hot and dense singularity. As a result, the inflationary rate of the universe expanded extraordinarily quickly. As inflation came to an end, that energy changed into matter, radiation, and antimatter, creating the remnants of the Big Bang that we can see today. This leads not only to a uniformly warm universe, with no evidence of a postulated grand, unified epoch in space and time, but it also predicts a particular kind and range of fluctuations in seed density. Surprisingly, observations supported these theories, showing that the entire observable universe, rich in the structure we recognize today, was formed naturally from what at first glance seemed to be empty space, albeit one that was packed with a significant quantity of field energy. The idea of creating the universe out of nothing is a powerful one, though not everyone will find it totally satisfying. There are many who feel that the concept of true nothingness is not connected to a universe that retains space and time, the laws of physics, fundamental constants, and some non-zero field energy inherent to the fabric of space. We can envision a world without boundaries, a time span beyond space, and a set of circumstances determined by the laws of physical reality. Philosophically speaking, these fantasies are legitimate since they view physical realities as components that should be removed in order to achieve true nothingness. There are 4 definitions for nothing in science that are valid depending on the context. Empty space-time in its lowest energy state, empty physical space, a time when your subject of interest did not exist, and whatever is left over after the universe and its laws are eliminated. Taking the first 2 definitions of nothingness into consideration, we can say with confidence that we have created the universe from nothing. However, it is not possible to make such a claim based on the 3rd definition. Sadly, we do not know enough to know how the 4th definition would work, in the absence of a physical theory explaining what exists outside the universe and outside the purview of physical laws. In the context of physics, the notion of true nothingness is intrinsically ambiguous. What does it mean to be a being that exists outside of time and space? Furthermore, how can time and space logically and predictably come into being from a state of non-existence? This viewpoint assumes that, despite the possibility that they are space, time, and the laws of physics are not eternal. Under the circumstances we would like to apply them, the validity of any theorems or proofs contradicting their eternality rests on assumptions that are not well established. The universe as we know it does appear to have started from nothing if you accept a physical definition of nothing. But when you throw away the physical limitations, all doubt about our ultimate cosmic origins disappears. Regretfully, any information imprinted from a previous state in our observable universe is wiped out by inflation by its very nature. We can only make inferences about things that can be tested in the domain of our physical reality, within the confines of our imaginations. Though many of the ideas, such as the idea of complete nothingness, make sense logically, they are still concepts that exist only in our imagination. Think about this. Could you ever make it back to your starting point on Earth if you traveled through space at the speed of your dreams in a straight line? It is surprising to learn that, on Earth, if you were to walk 40,000 kilometers in a straight line without taking into account obstacles like mountains and oceans, you would eventually return to your starting point. The Earth is finite and simply connected, even though it looks flat in comparison to your immediate surroundings. This implies that any loop drawn on it has the ability to be reduced to a single point. Similarly, the observable universe appears to be flat on all the scales we can study. Not even on the biggest cosmic scales that we can reach does there appear to be any spatial curvature. It's possible that the real universe is finite, even though it may be flat and infinitely extended in all directions beyond our current observable boundaries. It could be flat and barely connected, or it could be large-scale curved and a part of a multiply connected donut-like space. Recently, interest in this idea has grown again, but the important question still stands. Is this theory well supported by scientific data? Currently, a number of important observations form the foundation of our knowledge of the cosmos. The galaxies that are dispersed throughout the night sky and contain millions or billions of stars are located millions to billions of light years apart. The Milky Way is only one galaxy in our observable universe, which contains about 2 trillion galaxies. We see that the light from far-off galaxies undergoes a redshift, moving towards longer wavelengths as we look farther and farther into space. Taking this phenomenon and general relativity from Einstein together, we get the conclusion that the universe is expanding right now. This expansion suggests that the universe was hotter, denser, and more uniform at some point in the past. By going back in time, we can imagine a state of the universe where matter was so hot and densely packed that attempts by an electron and an atomic nucleus to form a neutral atom were always temporary. Soon after, a different particle or photon would come along with enough energy to cause the atom to ionize once more. When the universe cools down to the point where the remaining photons are unable to ionize the atoms, that is when things turn. At this point, the cosmic microwave background, or CMB, a remnant light from the Big Bang, becomes visible as the first light signal from the universe. Amazingly, this glow appears consistently from every angle, no matter where we are in space. The CMB is extremely uniform, deviating from the average temperature by only about 100 microkelvin, or roughly 1 part in 30,000, despite its current low temperature of 2.725 Kelvin. We can investigate whether there are scales beyond which variations in temperature abruptly disappear by looking at the features of regions of different sizes. One explanation for the existence of this scale could be the limited speed of light. Even if the universe has been expanding since the Big Bang, there ought to be a limit, particularly in the early stages of the universe, where no signals could have spread from one area to another, not even those moving at the cosmic speed limit. This expectation gives rise to the concept of a cut-off scale, which is also known as the cosmic horizon scale. Over this length, there should be no coherent temperature fluctuations left at all, and no super-horizon fluctuations. Super-horizon fluctuations, however, have been confirmed by observational data, notably the polarization data of the CMB, which was first gathered and then more precisely measured by Planck. This observation contradicts the theory that the Big Bang is the universe's single origin and provides strong evidence in favor of cosmic inflation. Information on how the magnitude of these fluctuations, that is, the variations between hot and cold spots and the average temperature changes with respect to angular size, is encoded in the cosmic microwave background, specifically in the temperature fluctuations rather than the polarization data. To understand this, imagine overlaying a CMB map with a circle of a given size, then finding the average temperature inside the circle. There are many regions to sample at smaller angular scales, but there are few at larger angular scales. The apparent size of these fluctuations, whether greater or smaller than their true sizes, depends on how space is curved. It appears that the entire observable universe is spatially flat based on our exact measurements, which we have made with a precision of exceeding 1 part in 250. This observation opens up a number of possibilities regarding the true nature of the universe. It could be infinitely long and never loop back on itself. It could have curvature, either positive or negative, like that of a horse's saddle, but on a scale so large that it appears flat at our observable scale. Or it could be finitely long and perfectly spatially flat, with a non-trivial multiply connected topology, appearing flat in all directions. It is interesting to investigate the possibility of a multiply connected topology, since it may have observable consequences. An approach to this research is to look for temperature patterns in one place that correlate to patterns in another location by analyzing the fluctuations in the cosmic microwave background. Repetitive patterns would appear in the CMB if the universe were smaller than the cosmic horizon and looped back on itself. If the universe does loop back, it appears to happen on scales greater than our ability to observe, as our searches for these features have turned up nothing. However, this leaves open the possibility that there is a connection between the universe's geometry and scales above the early cosmic horizon, where temperature fluctuations take place. According to inflation theory, temperature fluctuations were first introduced into the universe on all cosmic scales, and these fluctuations should have been roughly the same in magnitude on all scales. Larger scales should sustain a continuous spectrum of temperature fluctuations, while smaller scales, influenced by radiation pressure, gravitational pull, and photon normal matter collisions, would show peaks and valleys. But if we contrast our expectations for the universe with what we see, a subtle contradiction becomes apparent, and this is something that needs to be carefully examined. At the largest cosmic scales, that is, at angular scales of 60 degrees or greater, we find that the temperature variations, or the differences between the real and average temperatures, 2.725 Kelvin, are surprisingly smaller than expected. This is significantly smaller than expected. Instead of deviating by about 100 microkelvin, they only deviate by 20 to 30 microkelvin. Because of this disparity, astrophysicists and astronomers are investigating if there could be a physical explanation for this phenomenon. It is important to recognize that our predictions are statistical in nature, given the fictitious scenario of an infinite number of universes generated by processes akin to those in our own universe. But we are limited to studying a single universe, and the observed results become intrinsically constrained at the largest cosmic scales, where independent regions are few. Even though it is unlikely, roughly 1 in 800, or slightly better than 0.1%, to encounter a universe with such negligible temperature fluctuations on the largest angular scales, it is not unthinkable. It is not yet clear whether a physical mechanism could account for these unexpectedly small temperature fluctuations on these large cosmic scales, given the difficulty of drawing firm conclusions from such limited statistical samples. A research team proposed the novel hypothesis in 2003 that our universe may be shaped like a dodecahedron, a 12-sided regular polyhedron, in topological mathematics rather than having a smooth structure. This particular arrangement may be able to dampen temperature variations seen at the largest cosmic scales. This model helped bring a once obscure concept into the mainstream of science, even though some of its predictions did not come true exactly. Fundamentally, this concept rests on the idea that the universe is connected, with some circles resisting reduction beyond a certain length, rather than simply connected, where any drawn circle could be easily shrunk to a point. This characteristic may provide an explanation for the observed suppression of cosmic scale temperature variations. Now let us go back to the most recent study, which made headlines recently by bringing back an idea that was first proposed 18 years ago. Albeit in a slightly different format, this time the focus is on the idea that the universe has a torus topological shape, which is similar to a donut with a hole in the middle. Just as with the dodecahedron proposal, the torus idea has consequences for observational results. These consequences, meanwhile, depend on the size of the donut torus and are statistical in nature. Its predictions match observations more closely than those of a flat, simply connected universe, which necessitates a low likelihood of spontaneous realization if it's only slightly larger than the observable portion of our universe. Since it explains the suppressed power on these large angular scales, this is especially important. Although the concept of a universe shaped like a torus is fascinating, theoretical physics presents a significant obstacle to it. It is against the fundamental rule of persuasive theoretical ideas to introduce a new parameter just to explain one unexpected observation. For theoretical physicists, prediction accuracy is critical. Not only should a new theory build on the successes of the current one, but it should also explain observations that have gone unaccounted for in the past and offer new verifiable predictions that set it apart from the old one. But alas, a lot of proposals, the torus-shaped universe concept, recently included among them, fall into the trap of adding one new parameter to explain a single observation. It is our limited ability to observe that presents the true difficulty in comprehending the cosmos. There is only one universe that we can study, or more accurately, there is only one that is observable to us. Unlike repeatedly rolling dice, we do not have a large enough sample of universes to make meaningful comparisons. Our universe contains so few data points that it is difficult to draw firm conclusions or create a thorough understanding of its underlying principles. Our knowledge of the origin and nature of the universe is constantly changing as we travel through the cosmic landscape. We are making progress in solving cosmic mysteries through the interaction of theoretical frameworks, observational data, and philosophical considerations. Humanity's unwavering quest for knowledge is reflected in the quest to understand the universe from its primordial beginnings to the present, prompting us to consider the mysterious fabric of our cosmic existence. Click the like button or leave a comment below if you want to share your cosmic thoughts, or if you would like to hear more stories from the universe. We spent a great deal of time and energy creating this, so your support means the world to us. Allow us to carry on with our cosmic exploration, opening new chapters in the cosmic story.